All right, hello everyone. Welcome to the second part of the video for section 4.3, continuing studying this idea of critical values and how they'll help us to identify maximums and minimums of functions. Excuse me. Before we jump into the new learning, I just want to point out with this meme here, for those of you who don't know me, this is not actually how I look, the thing you see here in the picture. The difference is that I usually wear a red robe instead of the black one, so that's how you know this isn't me. Okay, so as I mentioned, we are continuing on with looking at how critical values help us identify maxima and minima. And in the last video, we talked about finding critical values and then talked about how they would relate to values generally where the slope of the tangent line is 0, which means then they relate to maximum and minima. And so now we have these two pieces of information here that'll explain to us now how we can use that information to identify maxima and minima on a function. So first one up there says that if we have a continuous function over an interval, the absolute maximum of the function over that interval and the absolute minimum of the function over that interval, there's two possibilities for where they could occur. They could either occur at endpoints of the interval. So we talked about if you're looking at like part of the domain of the function or the entire domain of the function, they could be at the endpoints or at the critical points. Okay. And so then how do we identify those? Well, we have this problem solving strategy that kind of walks us through how to do it. So first thing we'll do is evaluate the function at the endpoints. So we want to know if the two endpoints of our interval are a and b, we want to know what f of a and f of b is, because those could be where the maxima or minima occur. Then we find all critical points that lie within the interval, and notice that the interval is described with parentheses there between a and b. So we're looking for values between a and b that are critical points, not a or b themselves. And we evaluate the function at those points. And then we compare all of those values, and we look for one that's the largest and the smallest to help us identify the absolute max and the absolute min on that interval. Okay, so let's use this on a practice problem. And I should note at this point, for those of you who are watching this video during spring quarter of 2020, I had said there was going to be a classwork assignment on this section, and unfortunately that's not going to happen. I just don't have time to get it together. So the things that I said were practice. From the first video, I would suggest you try them yourself, but they will not be submitted for graded practice. Okay, so here we have to find the absolute minimum and maximum values of the function f of x equals 2x cubed minus 15x squared plus 100. And the interval we're given is -2 to 8, which means that this is our a comma b. Okay, so we're going to follow that process that was just outlined on the previous slide. So first step is we evaluate the function at those two endpoints. So we'll do f of -2 and f of 8. Okay. So plug those values in. If we plug in -2, I believe that what we will get, just checking my notes here, it looks like we will get -24. And then f of 8, if we plug that in, it looks like we'll get 164. And you guys can double check on me on that. Let me know if I made any mistakes. Okay, so first thing, evaluate the function at the endpoints. Next thing, step 2, find the critical points of this function. Okay, and remember to find the critical points, first thing we have to do, take the derivative. So we'll find f prime of x. This derivative, we can use the power rule here. So we'll have 6x squared minus 30x. And take the derivative of the 100, that gives us 0. And then to find the critical values, we look and see what values make the derivative undefined and or what values make it equal to 0. In this case, because we got a polynomial, As a derivative, there's not going to be any places where it's undefined, but we can find places where it equals 0, so we'll set this equal to 0. So 0 equals 6x squared minus 30x. We can factor some stuff over here on the right-hand side, so we can do 6x times x minus 5. And then we can take each of these pieces here now, because we have two things being multiplied, set them each equal to 0, and solve for the values of x. And if we do that, we'll end up with x equals 0 and x equals 5. Okay, so those will be our two critical values here. And then the last thing we have to do for this step is to plug those into the function. Now be careful, when we plug those in, we're going to plug them back into the original function, not the derivative. They're going back into the original function. Okay, so if we do that, what we will end up with here, we'll do f of 0. As you plug that in, we're going to get 100. If you plug in f of 5, then we get negative 25. Okay, and so that will complete step 2. And then step 3 from that process was to now compare these values. Okay, so look and see which are the largest and which ones are the smallest. So through this, I see that f of negative 2 is negative 24, f of 8 is 164, f of 0 is 100, f of 5 is negative 25. So first thing I see is that my max value here, okay, well that occurs over here with the input of 8. So it occurs at the point 8, 164. And the min value we end up with looks like that is this one here, right? When we input 5 and get an output of negative 25. Oops, write that in blue. And actually, let me, never enough space here. Okay, let me put a min. And that's going to be 5, negative 25. Okay? Now, a couple of things I want to point out about this. So we found, first of all, for the max, that the point where that happens is 8, 164. Now, if we were looking at a question or trying to figure out what is the maximum value that the function achieves over this interval negative 2 to 8, well, the answer to that would be 164, right? Because that's the output value, so that's the maximum value of the function on this interval. Similarly, we said that the minimum happens at the point 5, negative 25, but the minimum value of the function over this interval then is negative 25, because that's going to be the lowest value that the outputs reach over this interval. Okay. The last thing I want to point out is notice that when we did this, for the max, it happened when x equals 8, which was one of the endpoints of the interval. And we found the min, that was at x equals 5, which was one of the critical values. So this is why when you're identifying mins and maxes over a particular interval, and you're looking for absolute mins or absolute maxes, you not only have to check the critical points, but you also have to check the endpoints. Okay, I cannot iterate that enough. Check the critical points and the endpoints to figure out where your absolute min and absolute max are over over an interval. Now, if we're just looking for local mins and local maxes, okay, well then any of these answers would work, right? We would say that there's going to be some sort of min or max at negative 2, negative 24, some sort of min max at 0, 100, and also 5, negative 25, and 8, 164. The two that we've identified here, the 8, 164, and the 5, negative 25, those are the absolute min and the absolute max. And we'll learn in a later section in chapter 4 how to, if we just have a point, determine whether it's a min or a max without comparing it to other function values. Okay. All right, one more thing from this section. So the examples we've looked at between the last two videos about finding critical values, it's so far just been where the derivative equals 0, and I keep stressing that it's also where the derivative is undefined. So I want to show you an example of that. So here we have this function k of t equals square root of t plus 2. And when I find critical number or numbers here, so the first thing we need to do is take the derivatives. So we're going to find k prime of t. And first of all, because we have the root here, I'm going to rewrite this as t plus 2 to the 1/2. Just going to make it a little bit easier to find the derivative. So when I do that, I use the power rule, which is 1/2 times t plus 2. Subtract 1 from the 1/2 and end up with negative 1/2. And then we could use the chain rule to multiply by the derivative of the inside, the derivative of the t plus 2, but the derivative of that will just be 1. Okay, so to work this out, we end up with k prime of t. And noticing that there is a negative exponent here, I'm actually going to write this out without a negative exponent. So we'll have, let's see, 1/2. Yeah, 1/2 times the negative exponent means I could write this as 1 over t plus 2 to the 1/2, but the 1/2 we know means a root, and then times the 1 doesn't change anything. So we see that our derivative here is actually 1 over the square root of t plus 2. Okay? So now let's try to find the critical values. Now, first things first, trying to find the critical values, we want to figure out what makes this function equal to 0. So we would set 0 equal to 1 over 2 times the square root of t plus 2. Now, if you're not sure how to do this, one way to think about this is we have a fraction over here on the right-hand side that's equal to 0. And when you have some sort of a fraction, let's say it's a over b equal to 0, in order for that to happen, one of the two numbers here on the left, the a or the b, has to be 0. And which one is that? Right, the answer is a has to be equal to 0, right? The top of the fraction has to be equal to 0 in order for the fraction to be equal to 0. Well, here in our fraction, notice that our top number is 1. Will that ever be equal to 0? Will that ever be equal to 0? No, the answer is no, right? So in this case, there's actually no critical values we can find where the function equals 0. Okay, they just don't exist, or the derivative will never equal 0, actually. Okay, so now we go on to that other part, or that other criteria we look for when we're finding critical values, which is where the derivative is undefined. Now, when looking at our derivative formula here, can you see, are there values of t we could plug in that would make this undefined? Well, I see that there's a fraction, and we know that one of the big no-nos with fractions is that the denominator cannot be equal to 0. So in order to find those critical values, then what we can do is take that denominator, let's set it equal to 0. So do 2 times square root of t plus 2 equals 0. I can divide by 2. So I'll end up with square root of t plus 2 equals 0. Got to undo the square root so I can square both sides. So if I do that, I end up with t plus 2 equals 0. And hopefully you see from there, we'll get t equals -2 as our critical value. Okay, which hopefully you also see why that's a critical value, because if we plug that into the root here, you'd have -2 plus 2, which is 0. So square root of 0 is 0 times 2 is 0. So we'd have 1 over 0, which is not allowed. Okay, so this is an example of a function where a critical value is what makes the derivative undefined. Okay? All right, that's all I have for now. Thank you for watching.